so now is when we're going to introduce properly the bounded distortion condition, right? So we said that we want to show that SI satisfies this these continuity conditions. So we have lemma Sn cheating because I have the black color. Okay, so we're going to prove this for Sn. Once we have this for Sn, it will automatically imply for Hn because we're just taking the average. So, remember the bounded distortion so the picture that we always have here I'm sorry, I keep switching between Fi and Fn depending on the way I formulate it. So by the mean value theorem, we know that there exists, by the mean value theorem, there exists some psi n in omega n such that this ratio, so such that f this is the interval I. The size of I is equal to derivative psi n times the size of omega. And this, of course, is equal to 1. Now, what does the bounded distortion say? The bounded distortion says that really the derivative at any point in omega n is more or less the same. Right? So up to some multiplicative constant, so by bounded distortion, says that, in particular, says that log of Fn prime x over Fn prime y is less than equal to some constant, right? Which we don't really need a log, we can write it as Fn prime x Fn prime y is less than equal to exponential to the k, which is also just some uniform bound. Okay, which says that Fn prime of x is less than e k Fn prime of y greater than or equal e to the minus k Fn prime of y. Right, that's just what this means. this constant e to the k and e to the minus k is independent of everything, right? Is independent of x, y. Sorry, I didn't write it very well here. To like, give it a bit more space, because this is the key. So fn prime of x less than e to the k times fn prime of y less than e to the minus k fn prime of y. Right, so really what this bounded distortion is telling us is that the ratio of the derivatives at 2 points in the same branch is bounded by some constant. Okay, so the derivative at this point is comparable to the derivative at this point by up to some multiplicative constant, which is independent of n, all of the points, all of everything. Okay, so this derivative here is comparable to this derivative here up to that multiplicative constant. Okay, so this means that up to that multiplicative constant, I can replace this. Okay, so this, I can write this. So how shall I write it? I'm going to be a little bit hand waving here, okay, but basically what this means, and what this means is that how shall we write this? So let me write this as this means that this means that f n prime psi n is equal to 1 over omega n, right here. And what I'm saying is that the derivative at any point is uniformly comparable to this, and therefore is uniformly comparable to this. Okay? So therefore, we have that the derivative x is basically 1 over omega n, okay, for all x in omega n. Where this just means that it's greater than or less than equal to by a factor, by the multiplicative factor e to the k or e to the minus k. Okay, I write this as f n prime of x is like f n prime of y. Right, up to this multiplicative factor. So I like this. Okay, and then that's it. So then we have that then that's it, right? Because if you look at the derivative, so this means that so Sn of x, which is equal to the sum over all y in f minus n of x, right, is equal to 1 over the derivative fn prime in y and so each of these y's belongs to one of the omega n's, right? So when we look at f minus n, this is summing over all the three images, which means that you're summing exactly one y inside each of the omega n partition elements, right? So this is exactly equal to the sum over all omega n in Pn of y, which is f minus n of x intersection omega n, right, of 1 over fn prime of y. Okay, and then for each of these, as we just said here, this y, we don't know what the exact derivative is y, we don't need to, but we know that this is up to some constant, uniform constant bounded above and below. This is like 1 over omega n. So this is basically like the sum over omega in Pn of 1 over the size of omega n. Up to some constant, because the sum, the bound comes out of the sum, right? If you write it properly, you just get constants above and below, which you take the sum, that comes out of the sum, so we did this. And what is this? This is just the sum. These are all disjoint elements. They form the interval, so this is exactly to 1. Because this is just all these omega n's are disjoint, and they form a partition of the interval modulo 0. So this is exactly 1. So this means that this Sn of x is up to a constant, multiplicative constant bounded above and below equal to 1.
It's not the reciprocal at 1, it's not 1 over omega n.
Omega n, I'm sorry, of course, yes. That's the whole point. Yes, thank you. That's what we want. So it's precisely because omega n is a partition of, they're all disjoint, they form a partition of the interval, so it's exactly equal to 1. Thank you. So here finally we have used the bounded distortion in an essential way, right? How have we used the bounded distortion? We've used the bounded distortion to say this. And this also shows in what sense I keep emphasizing the bounded distortion is a relaxation of piecewise affine, right? Piecewise affine says that the derivative is constant on every branch. Here the derivative is not constant, but the bounded distortion says that the relation between the derivatives is boundable. So the derivatives at 2 points of the same branch, they cannot differ too much, right? This is what went wrong in that example when we had the neutral fixed point at 1, right? We failed the bounded distortion because you cannot have that, because the derivative of the fixed point is always 1. At some other point it will be arbitrarily large when n is large. So you cannot have this uniform. The point about this is that it's uniform in n. And so the fact that it's uniform tells us that the derivative is up to some bounded constant above and below, relate, basically the reciprocal of the size of omega n. And this then, together with the explicit form, so we've used in a fundamental way the fact that we have an explicit form, which of course is not fully explicit because we don't know exactly what the derivative is at this fixed point, but using the bounded distortion, we know that the derivative is roughly equal to 1 over the size of the partition elements, and that's how we get it. So this shows that the density of these push forwards is uniformly bounded away from 0 and infinity, right? On the whole interval 0, 1, which is the most important, in some sense, the most important property of this density. The next thing we need to show is that it's Lipschitz, right? We need to show that Sn is Lipschitz continuous. So now again we use to show Lipschitz. Again we will see that Fn prime of x over Fn prime of y is less than equal to, now we have a little bit, we use the stronger version. Remember that the way we formulated the boundary distortion is not just with k, but with Fn of x minus Fn of y. So what we really have here is k, and then we have Fn of x minus Fn of y. And we can write this as less than or equal to 1 plus some k tilde, since this is always less than 1, this is some constant times Fn of x minus Fn of y. And inverting these two, we also get this is 1 over, we can write this as 1 over, so because this holds for every x and y, right, and this is symmetric in x and y, then this is just 1 over 1 plus k tilde Fn of x minus Fn of y, which we can actually write as greater than or equal to 1 minus some other constant, let's put k double tilde, times Fn of x minus Fn of y. Okay, so this is just taking advantage of the boundary distortion to say that you can write this as the ratio, again, is close to 1 up to some constant that can be written in this way. And combining these two bounds, this implies that we can write actually so how do we want to write it? So this implies, I'm sorry, no, I shouldn't have written it as as the same thing, because this has one, yeah, it doesn't matter actually. Yes, so what we want to write here is that this implies that F sorry, okay, obvious. So this just means, so we take the 1, yeah, I don't know what I was saying. So this means that F prime of x over Fn prime of y minus 1. So this means that this is, they're both at this distance from 1. This means that this is less than or equal some k maximum between k tilde and k double tilde times Fn of x minus Fn of y. Okay, and that's all we need. Then again, it will be just one step, one line from this. Okay, so Sn of x minus Sn of y equals 2. So now we're just going to plug into this expression. We want to show this is Lipschitz continuous, right? So we just use the definitions of this. This is equal to the sum x tilde in f minus n of x of 1 over fn prime of x tilde minus the sum of y tilde in f minus n of y of 1 over fn prime of y tilde This is just the definition. And okay, in principle, there's not much you can do with two sums like this, but here notice that we do have an ordering, a natural ordering of these pre-images, right? So because everything is on the interval, even if there's an infinite number, even if there's a countable number, we can index this countable number, right? So we can write this as equal to the sum of x, it's the sum from I equals 1 to infinity of 1 over fn prime of xi tilde minus the sum I equals 1 to infinity of 1 over fn prime of y tilde I, okay, where x tilde I, y tilde I belongs to some omega r, omega n I for some indexing of the omega n's in Pn, right? So Pn is a countable partition into subintervals. Remember that in principle it may be very complicated, right? If it's a finite partition, this is obvious. If it's a finite partition, we can just look at the order of them, right? 1, 2, 3, 4. We can order them, and we can index these in such a way that xi and yi belong to the same partition element, right? And we can do the same thing here also. We can just index somehow these countable elements of the partition, and then we can rewrite this sum, okay, where we take the sum over all these pre-images indexed in a particular way, in a consistent way, indexed in a consistent way so that these belong to the same partition. So it's just reorganizing the sum in such a way that these pre-images are consistent. And the fact that they're consistent then allows us to take the sum out, right? Because this is of course just the sum I equals 1 to infinity, or this is less than or equal to the sum of 1 over fn prime x tilde I minus 1 over fn prime y tilde I. And now we can write this as we can pull this out, so we can write this as the sum I equals 1 to infinity of 1 over fn prime xi tilde times 1 minus fn prime x tilde I over fn prime y tilde I. Okay, I just rearrange the terms. And here, now we use this. So let's call this k hat. Right, so now we have x tilde I and y tilde I are in the same partition element, right? So of course, this is this bounded distortion. So maybe I didn't write it. So by bounded, so when I wrote this, what I meant is that by bounded distortion, I bounded distortion for all x, y inside some element omega n, you have this, right? So because the bounded distortion applies to elements inside the same omega n, so we have this, so we ended up with this, assuming that x and y belong to the same element n. And that's exactly what we have here. xi tilde and yi tilde belong to the same element of omega n. So this is less than or equal to less than or equal to k hat times the sum I equals 1 to infinity of 1 over n prime of x tilde I times fnx minus fny. But this here, recognize this. This is exactly Sn, right? Because here the sum from 1 to infinity is the sum, is exactly the sum of all three images of x. So this is exactly equal to k hat Sn in x times Fn of x minus Fn y. Sorry, sorry. This is Fn of xi tilde. Sorry, this is Xn of xi tilde. This is Xn of xi tilde, yi tilde. And of course, xi tilde and y tilde are just three images of x and y. Right? So this is exactly x minus y. So this is x minus y. And because we know that Sn is uniformly bounded, right, then we have that this is less than or equal some uniform constant x minus y, which is the Lipschitz property of S and x minus S and y. Because we just showed that n is uniformly bounded here. Right? So we get exactly this. Exactly this. So it's not easy to say really heuristically why you get this Lipschitz, but it's ultimately it is again we use in a fundamental way the boundary distortion property again, right? Because in the end we get this Sn term here, and then we get this term here, which is uniformly bounded by the boundary distortion property. And we use the fact that we have that slightly stronger boundary distortion property, right? So in these two cases we use weak. In this case we use a weaker version because we only use this, right? Which is a slightly weaker version. It doesn't have this fn of x minus fn of y on the right hand side here, but it's in many cases this is really the boundary distortion that is useful. In some cases you need a little bit, that little extra ingredient that you get by having this term here, and indeed we use it here to be able to get this, right? Which is what allows us in the end to get this. Otherwise we would just get that Snx minus Sny is less than or equal to Snx, which is a bound, which is less than a constant, but because of this we're able to get the x minus y here, which makes it Lipschitz, which is actually an important ingredient in then applying Pascal-Yard's law and getting the limit measure.